Now I'm going to give you an introduction to a new class of functions called exponential functions. Before we look at what exponential functions are, we're going to think back to linear functions and think back to one of the interpretations of linear functions. That'll be helpful for us to understand exponential functions, because we're going to use a different but kind of similar interpretation to give us exponential functions. Alright, so what is a linear function? Well, there's a lot of ways you can think about a linear function. One interpretation is if the input is changed by 1 unit, the output changes by a constant amount. In other words, you have a constant average rate of change. And that doesn't matter what the inputs are. Wherever your inputs are, your change in your inputs gives you the exact same change in your outputs. So suppose we have a function f, where f of 0 equals 3, and every time we increase x by 1 unit, f of x increases by 2 units. So x equals 0, we know what that is, that's given, f of 0 equals 3. For x equals 1, well, let me see, f of x is going to increase by 2 because we're increasing from 0 to 1. So if our output increases by 2, f of 1 gives us 3 plus 2, which equals 5. For x equals 2, that increases by 1 more, so our f of x increases by 2 more. So we get 3 plus 2 more. For x equals 3, going from 2 to 3, that increases our x by 1, which increases our f of x by 2 more. We add 2 more onto that total. And if you look at the pattern, our general pattern is all of them have a 3 in it, and then the number of 2's you have are dependent on what your x value is. So you get 2 times x. Whatever your x is, the number of 2's you have added onto that is x times those. All right, and of course that gives us a linear function with slope 2. So one way of thinking of linear function is the average rate of change is exactly the same no matter what your inputs are. So what is an exponential function? Well, our exponential function is going to sound very similar to what we had for a linear function, but there's going to be one little twist. So here our interpretation is if the input is changed by 1 unit, the output isn't going to be changed by the same amount every time, but the output changes by a constant percentage. And that doesn't matter what the inputs are. So let's see how this works out in practice. So suppose we have a function f, where f of 0 equals 10, and every time we increase the x by 1 unit, f of x increases by, not by a fixed amount, but by 3% of whatever that value is. So for instance, if we start at x equals 0, of course f of 0 equals 10. Going from 0 to 1, we're increasing our x by 1. That means we increase our f of x by 3%. So since f of x increases by 3%, that means we get f of 1 equals 10 plus 3% of 10, right? Because what we were at 10, we increased by 3% of that same amount, and that gives us 10.3 when we compute that. So for x equals 2, going from x1 to x equals 2, that increases x by 1. That means we increase our f of x by 3% more, but now it's not going to be 3% of 10 that we increase it by, because we were at 10.3, we increase it by 3% of 10.3. So we get 10.3 plus 10.3 times 3% of 10.3. And when we compute that, that gives us 10.609. Notice that between 0 and 1, we raised by 0.3. Between 1 and 2, we raised by a little over 0.3. So we don't have a constant rate of change, but we do have a constant percentage. And if we do the same thing for x equals 3, going from 2 to 3, we're increasing by 3%. And so we get 10.609 plus 3% of 10.609. And that gives us 10.92727. All right, so I want to actually look at this formula from a slightly different point of view. I'm going to simplify in a slightly different way. So when we went from 0 to 1 and f of x increases by 3%, the way we wrote it was 10 plus 3% of 10, so 0.03 times 10. Well, we just smushed that into one number because we were looking at what the numbers were. But another way you can look at it is both of those terms have a factor of 10 in them. So if we wanted to, we could factor out a 10. And this turns out to be kind of helpful in terms of finding a general formula. So if we factor out a 10, well, let's see. If we factor out a 10 out of that first term, which is a 10, we just get 1. If we factor a 10 out of 10 times 0.03, we get plus 0.03. And if we squish those two together, we get 10 times 1.03. which is a pretty nice little formula. Now, if we go to x equals 2, remember our f of x increases by 3% more. So that means we're going to take our 10 times 1.03 and increase it by 3% of that. So we're going to take our 10 times 1.03 and increase that by 10 times 1.03 times 3%. Now, if you notice those two terms, they do have a common factor, just like before. Different common factor. This time the common factor is 10 times 1.03, so we can factor that out. If we factor it out of that first term, we just end up with 1 again. If we factor out of the second term, interestingly enough, we end up with 0.03 again, just like we did before. So then if we simplify that, we get 10 times 1.03 times 1.03 again, which is 10 times 1.03 squared. Same process is going to work for x equals 3. We increase by 3% more. Now we have 10 times 1.03 squared plus 3% of 10 times 1.03 squared. And you can do the simplification on that. What we're going to end up with is 10 times 1.03 to the third. So in summary, f of 1 is equal to 10 times 1.03 to the 1. F of 2 is 10 times 1.03 to the 2. F of 3 is 10 times 1.03 to the 3. I think we have a pattern here. In general, f of x is going to be 10 times 1.03 to the x. And that's put in the form of our exponential function. So again, an exponential function is a function such that for each unit change of the inputs, the percent change of the outputs is constant. And the formula is f of x equals a times b to the x. Where in this case, a and b are constants. B has to actually be a positive constant because then otherwise taking b to the x is going to be a real headache. And b can't equal to 1, not because that's impossible for b to equal 1, but if it does equal 1, it turns out to be a super boring function. I'll have you plug that in, see if you can see why. All right, so now it's time for you to work on the in-class activities. The name of the file is Introduction to Exponential Functions.